Hello everyone, let's take a look at our next problem. Prove for a squared plus b squared equals c squared that a and b can't both be odd. So my thoughts here are this is going to have something to do with maybe like the mod. If I look at even numbers squared, if I look at even numbers, if a and b are both odd, then clearly this sum is going to be even, which means c has to be even. So if I look at the possible values of the last digit of an even number squared, and I look at the possible values of the last digit of odd numbers squared added together, that I can't possibly have agreement. That's my first instinct on how to move with this one. Okay, so even numbers squared. So an even number squared has to end in a 0, 4, or 6. Okay. Odd numbers squared has to end in a 1, 9, or 5. So if I add together two odd squares, now I don't think this is going to work. But I do have another idea as I'm sort of backtracking a little bit here. I'm just going to write out, if a and b are both odd, then we can represent a as one more than an even number. Same thing with b. Okay, so here's what we're going to do. Suppose a and b are odd. This means that a is equal to 2n plus 1 and b is equal to 2m plus 1 for some values of n and m. So then a squared plus b squared is 2n plus 1 squared plus 2m plus 1 squared. And so what's important here is the very last term, the fact that this is all, I have a multiple of 4 plus 2. Okay, so this says that a squared plus b squared mod 4 is equal to 2. But c must be an even number. If a and b are both odd, then c squared must be even, meaning that c is even. And this says that c squared mod 4 is equal to 0. And so we've got a contradiction there, right? The sum of two odd squares is equal to 2 mod 4. But c squared would have to be equal to 0 mod 4. So yeah, if you have a Pythagorean triple, at least one of these two on the left-hand side has to be even. Good question. Thanks for watching.